Another example for class, I think it's class 16, yeah. Better label it at some point. So this is problem 539, 555, I think. Actually, let me see what it is in this 11th edition, because that's what we're doing here. So in chapter 5, let's see. Well, actually, I probably need to look into chapter 3 in order to do this. Yeah. So it's actually problems 550 through 566, and it refers back to a problem in chapter 3. So in order to see which one it is, I believe this is problem 384 in chapter 3, and it's extending, therefore, this is actually, it's problem 555. Okay. So this is problem 555. I think, I guess it was 544 in the 10th edition, probably. Okay. So anyway, we have this problem. It gets used a lot. 3D shaft problem. We have 11 kilonewtons of force at A that's acting at 20 degrees. And there's another, so this is like an intermediate shaft on a two-stage gear, or maybe multi-stage, but at least two-stage gear, where we have a pinion that's sitting right above this, that's driving gear A with a total force of 11 kilonewtons. And there's another gear out of not shown that's attached to, that's being driven actually by gear B, and we're seeing the reaction, right? So B is driving another gear, but we're seeing the equal and opposite motion of force of another gear not shown that's acting on B. And this one is a 25 degree pressure angle, is what we call that. And so we don't know that yet, so we need to find. That's one of the first things we need to find. And we want to, and the material is 1018 cold drawn steel. And I also added a thing in here. Maybe I'm making this more complicated than it needed to be, but went ahead and did it. Said, okay, well, what if you put in a stress concentration here as well? And I said, well, it's going to be like a groove with a radius of 7 millimeters and a throat diameter of 47.5. So we'll show what that means here in a minute. So we started out, I'm just going to do the basic one where we have a 50 millimeter diameter shaft. And so here's the geometry with 50 millimeters to get the area, which we don't actually need. Moment of inertia and the polar moment of inertia. So here is the loads, which is quite often when we do one of these problems all the way through. It's like one of the first things we do. Maybe the geometry would be the first thing we do, but we get the loads. And so I need to find that unknown FB. So first off, I break down the force at A into the Z and Y components. That's going to be just a little easier, I think. We need to know it, so I might as well break them down. And then I do a free body diagram looking down the shaft, down the x-axis right here. And so you can see that 11 kilonewtons. We do the sum of the moments. Now we know it's only the force in the actual Z direction that's causing a moment here. The one in the Y direction goes through the center, so it doesn't do anything. And the same thing is true actually for FBZ, right? That one is only the tangential force is really causing moment. So I'm going to look for that FBZ using this, and notice the diameter is 600 millimeters and 300 millimeters, and I'm using the radius as the moment arm. So I get this unknown force here, FBZ, and then I get the FBY by multiplying it by the tangent of 25, right? So that's going to be the vertical component. And I don't actually need to know what FB is. I just need to know what FBZ and FBY is going to be. I do the same type of free body diagram, but now I cut the shaft so I could see inside, because I'm going to need the torque. So it's very repetitive. We've done this problem and problems like this a bunch of times. So this is just yet another example. But now we're going to do the same process we've been doing. We get the free body diagrams so that we can get these reactions at the bearings in two planes. Right, so we have the XY plane and the XZ plane. Set up the shear moment diagrams underneath it. So we did the statics, right? Some of the moments about O, so that we could find RCY. So we get that reaction. And then we do the sum of the forces, and we're going to get the other reaction at O, Roy, right? So we have the two reactions. And I went ahead and did the shear diagram next. So we have that first reaction creates this upwards shear, and then this force comes around as we're going from left to right, and doesn't go all the way down. Actually, it doesn't go below. This doesn't make it into negative. So it's a little bit. There's a little bit of positive shear, not much. And then we have this other force, and that of course brings it back down. So when we go to do the moment diagram of this, we have a sloping upwards, so that we get this value, and then it continues to slope upwards. And then when it gets down to B, it starts to slope downwards and goes to 0, of course, because there can't be any moments at the ends of these kinds of bearings. We're treating it as simply supported. And so we get the moment right here. And we do the same thing over on to the XZ plane. So we get the reaction at C. And then we do the sum of the forces in the Z direction, and we get the reaction at O. And then we're able to do the shear diagram right here, and it looks like this. And the moment diagram looks a little funky, right? Because it was positive here, and then all of a sudden it's negative, so it actually crosses 0 somewhere right around there. But we get a moment. It's not very large right here, but then we get a fairly substantial one right from this. And of course, remember that you could find this either in two ways. You could find the second moment. You could either take this 198, and then you take that negative 9845, multiply it by the 350 right here and subtract it from there, or you could go from the other direction, take that 10.83 kilonewtons and multiply it by my 300 millimeters, and the kilonewtons kills the millimeters, so we're going to be in Newton meters, and we're able to find this. So we want to get the total moment that's going to be acting at A. And so that's the square root of the sum of the moment here in this plane at A, and plus the squared, plus the moment here at A in this plane squared, and we're going to find that total moment. And we do the same thing at B, and it's substantially larger, right? Both. So as predicted, we would see that we would get a maximum moment of 4,097 right there. And is that what I use over here? Yes, it is. Okay. All right, it's not going to doesn't want to go to the next slide for some reason. Okay, anyway, we do like the stresses, and we find the bending, MC over I. Right, we have all of that, and it's 333.9 megapascals. Compression and tension, but we usually just use the tension side. And the torsional shear is TR over J, and we get 126 megapascals right there. All right, so here's the stress element. I didn't include that in the animation, but there's the summary of that stress element. Now we take the absolute maximum shear. Because this is uniaxial stress, as we see on our stress element, we can use this equation directly, right? We know that now, right? We could do more circle too, which is nothing wrong with that, and it's a good idea to do. But we do know from our experience that we can go straight to this equation and find that we have 209.4 absolute maximum shear. That would be the radius of the Mohr circle. We get von Mises. We can also use the uniaxial version of the equation, much easier equation than the longish other varieties of this when we have uniaxial. And we get 399. And then we get the safety factors, and we see that with the strength, by the way, we looked up that for that 1018 cold drawn was 370 yield strength. And we get 0.88, right? Only 2 decimal places in our final answer. For von Mises, we get 0.93, which we would predict. Okay, so I think at this point right here, I will show this right here. I have set up a spreadsheet for this. And what I'm going to do in the next part, I'm going to add my stress concentrations in here. But you can see that I have the yield strength and the diameter. I went ahead and input the torque and the moment. Some spreadsheets I'll actually have it so that I go from the very beginning of the forces and find the reactions and all that kind of stuff. But I just wanted to say I did this all by hand, put it in there. That's fine. I'm going to my moment of inertia, from that diameter, and polar moment of inertia, which is 2 times that. I'm putting 1 in for my stress concentrations, and then I find my moment. And I actually don't need the max of that right here. I'm going to fix my thing right there. Go boom. So anyway, this is my MC over I right here. And then I have my TR over J. All right, so I'm calling these the nominal ones, but then I'm going the maximum ones, which is just multiplying the nominal by the stress concentration. So putting those in there. And then I find my first principal stress and my second principal stress, because I might want to plot those. That's the reason why I find those. I might want to plot those on my failure loci, but I'm not going to this time. And then I have my absolute maximum shear, which is actually, you know, the sigma A minus sigma B over 2, right? But it's also the radius. We could also just use the equation. And then I have my von Mises. And we're going to show this in a second, that this is going to be useful to us, but I just want to show you before we went any further that I made a spreadsheet that I made sure was going to work, right, for results that I knew the answer to, because this is a problem in the book. We could probably have looked this up. Let's see. We said it was problem 555, so let's see if we have the answer in the back of the book to this one. It's always nice to look. I haven't looked. 555. No, they didn't do that one. Wouldn't you know it? But anyway, this one doesn't pass, right? It doesn't even have a safety factor of 1. So we're going to probably need to do something about it. It's already bad. But let's go ahead and do our what if thing, because we have stress concentrations, and this is another example where we're going to try to see value what happens with the stress concentration. All right, so this is the what if scenario where I have my 47.5 millimeter at the root. That's going to be my D right here, and I'm going to have a radius of 7 millimeters. So I'm going to repeat this with the different loading types here. Notice that this is a smaller diameter, so I have to actually get a different moment of inertia and polar moment of inertia, right? So you use 47.5 instead. And the stresses, so we have a different nominal stress than we were going to have before, right? So if I was going to do my spreadsheet right here, I take and go 0.0475, boom. And you can see here are the stresses right there, 389 and 147. There you go. Woo, I got it right. It's almost as if I used the spreadsheet. Now we want to get the stress concentrations. I look up in table 8, A1514 and A1515 for these. And here's the diameter and the radius over the diameter that I use. And I picked these numbers on purpose, so at least I picked the 47.5. So it would be something easier. I should have probably picked something instead of 7, something to make it 0.15 would have been nice. Anyway, so here they are on the stress concentration. You know, I'm using 1.05, so we have 1.05. We have that curve pretty close to it, and we have 0.14. So hereabouts is what I'm coming up with on that one, and hereabouts for here. So I decided this is 1.57 on this, and so I have a stress. I have a bending stress, maximum bending stress because of stress concentration of 611.3, and then I have a torsion stress concentration 1.28, so I have a total torsional shear of 188.7. So I want to combine these stresses onto a stress element and then do the absolute maximum shear. I get 359.2, and for von Mises I get 693.2. That's pretty substantial, right? A little big increase, but also we made the diameter kind of smaller because of these little grooves. So the safety factor drops a whole lot, and in both of these. And I could also do my spreadsheet over here. And let's see, in my spreadsheet, let's see, what did I say I made these for the stress concentration? Let's look back up there. Back it up, okay. So I said I had 157, 1.57, and 1.28. Boom. Okay. So looks like, did I get the right numbers? I think I got the right numbers. Let me see. Let's see. Did I get the same numbers? Yeah, I should have. Yeah. Okay. Yep. So everything's working. Something I should mention about the spreadsheet as well. Notice that I have how I've documented this, right? I've used my symbols and my units. I explain what the thing is, and I tell it where the source is for the equation. It's very good document stuff. It's important, to communicate, but also to just have a record of what you're doing, especially in a spreadsheet. A lot of times, you might come back to a spreadsheet that you haven't used in a long time. And so I want to look at an FEA let's look at both conditions right here and make a comparison of what we've done. And this is a long video, but I think it'd be useful. I don't know. So anyway, I made this scenario right here, right? So let's take, I think it's maybe easiest to use this image. I even in my spreadsheet have put in the original problem right in there, but let's take a look at this thing. You can see that there's a bearing right there, so I need to represent that bearing somehow. I also, in my FEA, need a place to hold this that's going to be correct, and I want 400 millimeters in between where this gear is, and 350 between the two gears, and then 300 over there. So I'm going to choose 25 millimeters as like the length of a bearing, and that's where the 400 is going to start. Right here, right? So let's see, I'll go back in time and I can show that that's what I did. I started out with 25 millimeters, and then I made a plane, and then I extended this 400 millimeters, and then I added actually two planes. I'll turn the planes on, I'll show you. I added a plane right there, and then I added a plane to either side of this, right? So you can see, and I made so it's 12.5 to each side of the center of the gear, right? And then I extended it out that 350, right? So it's going to 350 a little bit further, and then I did the same thing with two more planes, right there, right? So that's 12.5 to 12.5 on either side, and then I extended it out the final 300. And then I made a plane right there where that ended. And then I extended out another 25 right there, right? So you can see that I have planes on all the spots. Now I use those planes as split lines. So I've cut that shaft. I've just made an etching on the outside edge of the shaft in those places. And we can hide the planes, so I can display planes. No, I think it's hide show planes. Where'd you go? There you go, right there. Boom. Okay, hide. So I made a static study right here, and I applied them. Now I've applied these bearing supports. So let's take a look at those bearing supports. I made the material 1020 because I didn't have 1018, but it didn't really matter. It's going to matter with respect to deflection, but it won't matter in terms of stress. So I edit this, and I'll show you that this bearing support right here. One thing, I hit this little stabilize shaft rotation, and I allow self-alignment, right? So that means that it's not going to support a moment. So it's going to treat this like a pinned connection, which is what we want. That's important. And I don't know how exactly I would do this necessarily if I didn't have this preloaded bearing function, bearing support as one of my fixtures, right? If I look right there, you'll see that bearing was one of my fixture choices. I had to put a lot of thought into it to make this thing so it actually kind of acts pinned. And then I put the other bearing support right there, so two separate ones. For the loads, let's say open this up and take a look. First off, I use the right plane as my reference right here, and you can see that I have that force placed in there, and this force going down, right? So here is in the Z direction, and I have it aligned. I have that 10,340. So just to show you, this is how I place on there. And I did the same thing for this gear right here. And then for the torque, let's see, I used not only this face, but I also used the face to establish the direction. And here's my torque, and I'm going that direction in it. And you can kind of see these are the arrows right there indicating my torque. And I did the same thing here, but I made it go the opposite direction. Now, there could be some numerical problems with that because you need to have something fully constrained. I think it's just potential to have some problems because you remember that this thing is doing a numerical process where it's taking an estimate and fixing error. So if these things don't balance out, it could have a numerical explosion. Even though that you made them the exact same numbers right in here, it's by the way of this matrix needs to be able to be solved. Okay, so you just be on alert that like you might actually need to trick it sometimes by like holding one node in the rotation like at the end just to keep the thing from exploding because it might divide by 0 somewhere and get all angry at you. These kinds of things, but they probably built some stuff. I think that I suspect but don't know this one thing in the bearing support where they say stabilize shaft rotation. That might actually be like that stabilizing thing. They might throw something in there just to prevent that numerical blowing up of the thing not being exactly equal. So anyway, I solved it, and I gave it a crude mesh, and you can see I get 380.7, whereas I was predicting, this is before the stress concentration, so and this is von Mises stress. Let's see if I can get back up there. 399, not bad. I don't think it's bad. 399 versus 380. We're looking pretty good, and taking a look at this. Here's it looking from the end right there. You can kind of see how it's coming up in two planes, right? It's bending in two different directions. You can see it from the z direction. You can also see, so Les is looking at it from the side, and then we can look at it from above too by looking at the y-axis. So you can kind of see. And this deflection is an important thing, and we need to talk about it soon as in terms of our shaft design project. But this is these are pretty meaningful results. I could remesh this. This was just the crudest mesh. I just did not the crudest mesh, but I did a fairly coarse mesh. I'm going to try it again. Let's mesh it here. The video is going to be long, so you could just zoom to the end if you want to, but we could just run the thing and see what kind of difference it's going to make. Probably won't make a whole lot of difference. That's my prediction. I don't think we'll get to the 399 necessarily, but we might. There you go. We actually went down some, 379.6. But there are some approximations going on. Like my bearings, tell you the truth, I should have been at the center maybe of the support. The center of the bearing should have probably been where I started instead of like at the end of the bearing. But did the best I could. So it's probably, I don't know. It actually might get a lot larger. I think I would have a larger because of that error in modeling. But anyway, let's take a look at what happens with these grooves now, what I've done with the grooves. All right, so I modeled these grooves. You could see, let me show you how I made them. That's sort of like an interesting thing right here. Okay, so we'll look at that, the sketch, and this is remember there's 7 millimeter radius, so I made a 14 diameter circle, and I offset the point of that thing at 23.75, right? So that's 1/2 of 47.5. So that's the means at which we got the, and I put them dead center of where the gear would be. I know it's kind of a weird place to have this groove, but it was just it's just messing with the thing. So I put everything on there the same, except that maybe I put the forces and torques to either side of this piece right here. And then we show our results, and I get 562.8. I should maybe show the mesh. Let's see, where's show mesh. You can see that I made some amount of mesh refinement right down there, and if I wanted to, I could edit that control. I'm already set it like really fine, but I can make them even smaller. You can't go down too low. It won't blow. It won't mesh correctly. If you make it just keep going down and down. There's going to be a limit at which it won't do. I might have reached that limit too, by the way. And once it does that, it doesn't like to mesh. You could have all kinds of problems. But you could see, oh, look how fine that mesh is going to be. And we could run this again. And I might make another video for the redesign. Yeah, I'm gonna make a redesign video. So I'm gonna pick up where I left off on this after I get done with this part right here. I'll show you from my spreadsheet how we're gonna do that. So that's gonna be like a whole separate topic. Ooh, what happened? Oh, because it's deformation. There you go. And 577. So I didn't really get up to what we would predict. What I had predicted with our stress concentration was significantly higher here. Let's see where this guy is getting graphics bugs right here. See, at 693, that's the one that should be in agreement with my, not this one, but this one right here, right? So this is the one that we just, we should show that stress. Yep, so we're significantly off, but I didn't really expect it to be exact, but we're in the ballpark, 577.9. You can kind of see where that stress is hitting, right? Where that stress is being created, right in there. And actually on the compression side, doesn't look like. You would think it would be on the tension side, but on the compression side. So I'm going to end the video because it's going to be too long and not going to be as useful. But I'm going to pick up with another video where I'm going to redesign this shaft, and we could redesign it either with these stress concentrations or without it. But we want to just to have that experience of redesigning. So I'm going to be